the previous class, when we had run the simulation, we had noticed that the top red color curve, which is corresponding to the voltage, and the bottom corresponding to the current, there are some observations, and we are going to build on these observations. Okay. The first thing that we noticed was there is a voltage wave traveling to the right and to the left, because the source was kept somewhere in the middle for us to understand this a little bit more. What we immediately noticed was that the current moving to the right is having a positive amplitude, right, and the current going to the left is having a negative amplitude. So, we need to sort this out first, right, before sorting out the boundary conditions. Okay. So, I will start with this, go back to the nodes. Okay. So, in this case, the voltage, which was a function of position and time, okay, was traveling backwards, all right. If we consider the forward axis to be going from left to right, just because of the way we position the source, which was very unnatural for a practical experiment, but in simulation you could always do it, you saw the voltage wave going in the opposite direction. So, this means that you can call this to be a backward wave of the form f minus of t plus z by u, right. When we looked at the general solution to the wave equation, we had two terms for the voltage, f plus of t minus z by u plus f minus of t plus z by u. We are looking at the case specifically where the voltage is traveling backward. Okay. So, let us go ahead and make some manipulations. The idea is, given this to be the voltage, what is the current and what is the inference. Okay. So, we can write down the telegrapher's equation, where we have dou v by dou z is equal to minus L dou I dou t. Okay. This is one of the telegrapher's equations. The procedure that we will follow is similar to what we had done before for proving that the general solution is valid. We can use a change of variables method. Okay. Here we are having two independent variables. We will reduce that to single independent variable, do some manipulations, and then substitute it back. So, what we mean is, let a variable s be equal to t plus z by u. Okay. If this is the case, the function will become a function of single independent variable. So, you can call this as f minus of s. Since it is a variable, since it is the function of only one independent variable, I will simply be referring to this as f minus. Okay. So, now let us take the left hand side of the telegrapher's equation. Okay. So, I have dou v by dou z. Okay. I can write this down as dv ds and dou s by dou z. Okay. Since the voltage is f minus is what we have taken, so you can also write this as df minus ds, and dou s by dou z, if s is equal to t plus z by u, you will just end up getting 1 by u. Okay. So, we have dou v by dou z to be equal to df minus ds multiplied by minus 1 by u, where u is the velocity. Right. The right hand side is minus L dou I dou t. So, we can start with what is dou I dou t. Okay. So, we can write this as di ds times dou s dou t. Okay. Okay. Di ds times dou s dou t, s is equal to t plus z by u, is equal to 1, right. So, multiplied by 1, this is simply di ds. Okay. And the telegrapher's equation says that LHS is equal to RHS. implies df minus by ds, right, into 1 by u is going to be di by ds. Okay. So now all we need to do is find out I from here, all right. Since it's a direct one dimensional ordinary differential equation, all you need to do is find out the value of function of current. So I is going to look like minus 1 by Lu f minus of s, right, or you can simply write this down as minus 1 by Lu f minus of t plus z by u. Okay. So here it is abundantly clear that if you have a backward travelling voltage wave, the method of calculating current is slightly different. Okay. Since we are looking at this equation in the form of Ohm's law, you can say I is equal to V divided by R, but it looks like Lu will have the unit of characteristic resistance or ohms, but you are going to have minus 1 divided by Rc or characteristic resistance multiplied by the voltage, right. So in other words, okay, I is going to look like minus 1 by Rc, where Rc is the characteristic resistance of your transmission line times f minus of t plus z by u. Okay. You could also write this down as minus 1 by Rc times V of z comma t. Okay. This is a rewritten form of Ohm's law, but I wanted to put this clearly so that you know why the current is flipped when traveling on the left hand side. Okay. It is a consequence of the telegrapher's equation itself. Okay. So it is a very critical thing that you will have to bear in mind. Okay. And this has more consequences as we go along the course. Okay. So for the forward traveling voltage wave, the current will be simply 1 by Rc times V of z comma t, but for the backward traveling voltage wave, the current will look like minus 1 by Rc V of z comma t, which means that if you have to write down the expression for the total current in your transmission line, you will be having some positive current for the forward traveling, all right, minus some current going in the other way. So in the case of the general solution for the voltage, you had f plus of t minus z by u plus f minus of t plus z by u, but here you will be having 1 by Rc times f plus of t minus z by u minus 1 by Rc f minus of t plus z by u. So the general solution is slightly different for the current. One has to keep this in mind. Okay. That's why when we ran the simulation, the impulse at the starting point itself, you would have noticed that along the positive direction the voltage was positive and the current was also positive. So let's go back to that once again. Okay. But as there is an impulse going to the left hand side, you are having the current to be flipped. Okay. So this is the first thing. The second thing that we were noticing in the other class was that as it goes and hits the boundaries, something starts to happen. We were starting to see reflections, and the reflections were altering both the, reflections were altering the sign of the voltage or the current also. We need to start to look at this in more detail. Right. So I'll start with a circuit diagram that will allow me to do this. Okay. So I'm having a source voltage of Vs. Okay. And I'm having a series internal resistance, say Rs. Okay. And I'm having a switch that closes at time t equal to 0, and I have a transmission line The other end of the transmission line is connected to a resistance. The value of the resistance is RL. Okay. In order to indicate that I am dealing with transmission lines, I will make some subtle changes to my circuit diagram. First of all, I have marked some regions with circles over here to indicate something. On top of that, I can also say that its characteristic resistance is RC, velocity is u meters per second. I can also say that the length of the transmission line is going to be L, and to be precise, one can always say that you will have to mark this to be 0 of your transmission line and L of your transmission line. Okay. Okay. So, here what we are going to do is we are going to close the switch at t equal to 0, and then at steady state we are going to try and calculate the value of the voltage in your transmission line. So, the equivalent circuit of your transmission line in steady state DC will be really simple. Your capacitor will get open circuited, your inductor will get short circuited, correct. So, it is going to be easy to imagine what will happen in DC. So, we can say that V of z comma t, we know the general solution is going to be some V plus of z comma t plus V minus of z comma t, okay. And the corresponding value of current in your transmission line is going to be 1 by characteristic resistance time V plus of z comma t minus 1 by RC V minus of z comma t. Okay. This is how the voltages and the currents are going to be in the transmission line. Okay. Now, let us zoom into the part where the load resistor is connected. Okay. Let us focus this part. Let us more closely look at the load end, all right. You will be having some forward voltage going towards the load. We can call this as V plus of z comma t. Since this is a finite transmission line of length L, you will have some backward travelling voltage after it hits the load. Okay. So, we can call this as V minus of z comma t. Okay. Now, the reflection coefficient is defined as is given by V minus divided by V plus. Okay. It's the value of the voltage that is travelling backward to the value of the voltage that is travelling forward. Conventionally, the letter, Greek letter that is used to represent the reflection coefficient is gamma, capital gamma. Okay. So, V minus divided by V plus is the reflection coefficient, and let us look at the load end. So, I am going to start with that the position Z is equal to L. Okay. So, I will also mark what my Z axis is. This is my Z axis, right. At Z equal to 0, I will be at the source end. At Z equal to L, I will be at the load end. Okay. So, at Z equal to L, okay, I can write down the voltage at position L comma T or V of Z comma T, Z is equal to L, right, is going to be equal to Ohm's law, right, RL times IL or I of L comma T. Right. At the load end, I am just applying Ohm's law. The voltage is going to be equal to current times the resistance at the load. Okay. We can write the expansion for the voltage at that position. You will have a forward voltage V plus and you will have a backward voltage V minus. So, the left hand side has to be written as a superposition of a forward, right, V plus of L comma T plus V minus of L comma T is going to be equal to RL times, you will have to write down the expression for I of L comma T. So, we have already written this. So, it is going to be 1 by RC V plus of L comma T minus 1 by RC times V minus of L comma T. Okay. One can go ahead and rearrange this equation. Right. You will have V minus is equal to RL minus RC divided by RL plus RC times V plus. I am not going through all the steps, you can do the rearrangement on your own. Right. And the reflection coefficient I will be very specific at the load end. Right. So, to indicate that I am at the load end, I will just mark as gamma at z equal to L, all right, is equal to RL minus RC divided by RL plus RC. Okay. Now, this is the expression for the reflection coefficient that you have at the load end when your load resistor is RL and your characteristic resistance is RC. There are a number of things that this that can be interpreted from this. First of all, the numerator has a negative sign in between two terms. So, there is a good chance that your gamma can be positive, gamma can be negative, or gamma can be 0. Okay. So, we will write down these three conditions. Okay. You can say that if RL is much greater than the characteristic resistance, okay, you can say that so your reflection coefficient is going to be equal to 1 if your RL is much greater than RC. In even more practical terms, you can think that if your load resistor is not even connected and there is an open circuit in your transmission line and on the other side, your reflection coefficient is going to be equal to 1. Okay. Now, this reflection coefficient also needs little bit more explanation as to what we are doing. The reflection coefficient here is corresponding to V minus divided by V plus. So, a more clearer way of saying that is a voltage reflection coefficient. So, generally when people talk about reflection coefficient, they are talking about the voltage reflection coefficient. Okay. So, it means that the reflected voltage wave will have the same sign as the forward wave that was going to the load resistor. Okay. If RL is very much less than RC, okay, then your gamma L will become minus 1, okay, which means that if at the load end your say load resistor becomes 0, in other words you are shorting the ends of the transmission line conductors, you will have a voltage reflection coefficient of minus 1. Okay. And if RL is equal to RC, gamma L is equal to 0. Okay. Means that there is no reflection or no backward wave traveling from the load back into your transmission line. Okay. These are the three cases that are possible with the reflection coefficient. Now, we can have a look at our simulation and decide what is going on. Okay. We can go back to your simulation, fire it, and just look at what we expect the voltage reflection coefficient to be on each side. Let us just do this very quickly, right. So, I will just make this okay. Let us concentrate only on the voltage on the left hand side, it did not flip. Okay. On the right hand side, the voltage flipped. In between something happened here also, right. Okay. So, let me reduce the amount of time to prevent that from happening, but let us also, I think we can keep track of what happened. the impulse went to the left side, it didn't flip. Okay, that means your gamma was +1. All right, that means on the left hand side your RL was very much greater than RC, or you can say that on the left hand side you had an open circuit condition according to the way we have programmed. On the right hand side the voltage actually flipped. If it flipped, your reflection coefficient was -1. Okay, that means on the right hand side you had a condition of RL very much less than RC, or you had a short circuit condition. Remember that we had two different boundary conditions for simulating this particular section of the transmission line. On the left hand side we have imposed one condition, on the right hand side we have imposed the opposite condition. Okay. Now this also has an impact on the way the current is going to be flipping back and forth, okay, and correspondingly one can calculate current reflection coefficients, but you can derive the current reflection coefficient from the voltage reflection coefficient, because you can apply your Ohm's law and also the sign changes for your forward and backward currents, and you will be able to figure out what's going on. So if one were to look at this transmission line section and try to derive information, okay, we can always say that the right hand side was having maybe a short circuit or open circuit, I don't remember. On the left hand side it was the other case. Right. What is the use of such a scenario? Suppose you are having a very long transmission line, all right, and the transmission line is not functioning correctly, that is there is no data being sent to the other side, all right, and we want to identify at what distance what kind of fault has occurred on the transmission line. This could be say an underwater or undersea transmission line connecting two different continents, all right, it's very exaggerated, but it would be wise for us to figure out where the problem has occurred. Maybe the transmission line is broken, or maybe it is broken or the insulation is breaking down and something is shorting the forward and the backward conductor, all right. If we know the location and if we know the kind of fault that we are looking for, then it makes it easy for us to go to that particular place and fix something. Okay. So what people can do is they can take a transmission line, launch some voltage from one side, wait for the echo from the other side. If it is not flipped, then they know that it is corresponding to gamma is equal to 1, or the load resistance is going to be open circuit. So there is a breakage of the transmission line somewhere. We also know that the velocity in the transmission line is going to be equal to u. So you take the time at which you sent the pulse, all right, you will calculate the amount of time for you to receive the first echo, and then figure out how much distance it traveled two ways, and then figure out the location of the fault. So it gives you the location of the fault and the kind of fault that has occurred. The same thing can be done for the short circuit also. This method of finding out a fault in a transmission line is known as time domain reflectometry. Okay, all you are doing is launching a pulse, waiting for the reflection, and then you are trying to figure out what the reflection can tell you. Tells you typically what kind of fault has occurred and at which location. So this is known as time domain reflectometry. There is a lot of research that happens with time domain reflectometry. Here we are considering the very ideal cases, all right. In reality, there will be losses in the transmission line. There will be other parameters that you will have to consider, for example, dispersion of the line and all that. But in the simplest form, this is it. Okay, it's a time of flight measurement, and you also figure out what kind of fault you are having on the other end. Okay. Now, having gone this far, okay, we can take a small example and try to push the boundaries of what we know. Okay. So let's try to work out a problem with some small numerical quantities plugged into it, and apart from all these things, can we figure out something else? Okay. So I'll write down the formulation of the problem. It's a very simple problem. It says that I'm having a voltage of say 30 volts on one side. Let's say that there is a weird condition that the series resistance is very, very low or almost 0. I have a switch that closes at t equal to 0. Okay. I have a transmission line. And I have a load resistance. Okay. I'm going to write down the value of the load resistance that's given is 100 ohms. Okay. And in order to specify that this is a transmission line, some other information is added to it. L is equal to 2.5 millihenries per meter. C is equal to 1 microfarad per meter. Okay. And the length is given to be 400 meters. It's a long distance. Okay. So there are a lot of things that can be calculated. So I'll ask the question each time and I'll then mark the solution. Okay. So if you want to write down, draw the equivalent circuit ladder equivalent, all right, for one unit cell, you will draw a series inductor of 2.5 millihenry per meter and a parallel capacitor. So we can start with that. We know the equivalent circuit of a lossless transmission line. So if we have to draw the unit cell of a ladder, you can say that it will look like so this looks like 2.5 millihenries per meter. This is 1 microfarad per meter. Okay. The second thing that we can calculate from L and C is we can calculate the velocity. We know that the velocity u is going to be 1 by square root LC. That's 1 by square root of 2.5 times 10 to the negative 3 times 1 times 10 to the negative 6. That's, I don't know the value, how much we are getting. So it will be 5, so some 2 times 10 to the 4. Okay. 2 times 10 to the power 4 meters per second. Okay. The next thing that we can calculate from this transmission line, from whatever we have learned, is there is going to be a transit time. All right, it's going to take a finite time because the velocity is 2 times 10 to the power 4 meter per second. If you launch a signal on the left hand side, what's the time at which it's going to the other end of the transmission line? So we can calculate the transit time tau. Okay, transit time tau is going to be L divided by U. L is given as 400 meters, and this is 2 times 10 to the power 4 meters per second. Okay, that comes to it's 20 milliseconds. Okay, and we can go ahead and calculate a few more things from whatever we know. All right, let's say that we want to calculate the load reflection coefficient gamma L. It's RL minus RC divided by RL plus RC. All right. First of all, we need to estimate RC. Okay. The value of RC can be determined because we know the value of L and C. All right. So in this case, it is going to be 50 ohms. That's how I have made it. Right. So this is going to be 100 minus 50 divided by 100 plus 50. Okay. So square root of L by C, 2.5 millihenry per meter divided by 1 microfarad, that will become 50 ohms. Okay. So 100 minus 50 by 100 plus 50, which means that the reflection coefficient is going to be positive and it is going to be of the value 1/3. Okay. Now there is one more question that we can ask that we have not seen. So the idea is to keep building up on whatever we know, right? Granted that we have calculated the reflection coefficient on the load end. Okay. Now there is going to be a backward wave traveling from the load towards the source. Okay. Is it possible that as it comes to the left hand side edge of the transmission line, again some portion of it will get transmitted, some portion of it will get reflected, all right. So there is going to be a reflection coefficient on that edge also, right. So we can call this as gamma suffix s, or at the source, all right, end of the transmission line, all right. And that is going to be, you will just replace RL with your series resistance of the battery. In this case, we don't have a series resistance, so I'll just write this as RS minus RC by RS plus RC. Okay. And the series resistance of the battery in the way we have drawn is 0. Okay. 0 minus 50 by 0 plus 50, that is equal to minus 1. So, at the source end the reflection coefficient is minus 1. Okay. So, there are other things that can happen also, alright. So, that means that here you will be launching a voltage, okay, on the left hand side of the transmission line. It will go to the load, 2/3 of it will get transmitted, 1/3 of it is going to get reflected back. So, that 1/3 is going to come entirely to the other side of the transmission line, flip in its amplitude and go to the right hand side again. Once it reaches the right hand side, 1/3 of it is going to get reflected back and then it is going to flip, and so the voltage profile in a transmission line for such a simple circuit is going to change with respect to time, alright. It is going to change dramatically, alright. And one of the ways to track what is happening in the transmission line is by drawing what are known as bounce diagrams, okay. Okay, you can start with the bounce diagram. So, the bounce diagram, you will start with the length of the transmission line, say marked on the top like this. So, this will be your 400-meter long transmission line. Okay. The left hand side of the transmission line is connected to the source end, the right hand side is connected to the load end. Okay. The y axis is marked downwards, okay, and it represents time, unit of transit times. So, instead of unit of seconds, you will have 1 transit time, 2 transit time, 3 transit time, etc. Okay. So, the way it is constructed is, first you will have a transit time, say marked as tau, 2 tau, 3 tau, say 4 tau. Let us do it for 6 transit times. Okay. On the other side also you will have an axis, it is going to denote your transit time, and the way we do this is we just make arrow plots going from one side to the other side. Okay. In one transit time, okay, the voltage on the left hand side, here you are going to be launching some 30 volts, will reach the other side of the transmission line. So, what we do is we take the coordinate corresponding to one transit time on the other side. So, it is going to be here, and we draw a line connecting this, and we mark an arrow saying that the voltage is traveling in this direction in the transmission line. Okay. And in order to be clear about the value, you can just indicate the value as 30 volts traveling from left to right the transmission line. Once it hits the load end, okay, it sees a reflection coefficient gamma L equal to 1/3 or minus 1/3, 1/3. Okay, sees a reflection coefficient of 1/3, all right. So, the next transit time, 1/3 of it is going to go towards the source end of the transmission line. Okay. So, I can go ahead and connect these two. 1/3 will mean that this will become 10 volts. Okay. And once it reaches the source end, there is going to be a reflection coefficient again. So, I will write gamma S is equal to minus 1. Right. So, I will be having minus 10 volts going to the other side. Okay. And then you will have a reflection coefficient of 1/3. So, I will be having minus 3.3333 volts. Okay. Once again, the reflection coefficient at the source is going to be minus 1. So, I will be having and it keeps going. You can also, we have marked 6 transit times, so let's just finish this diagram for the 6 transit times. 1.1111. This is what is known as a bounce diagram, right? So you could be given, say, a set of parameters for the transmission line, like a circuit has been drawn here, and you could be asked to find out, draw the bounce diagram. So you will have to find out the reflection coefficient at the source, reflection coefficient at the end. You will have to find out what is the transit time, all right, and then you will have to construct these this diagram, right. You can also ask a question actually. You can say that at a position 200 meters from the source, right, which happens to be the midpoint of this transmission line. Okay. At a position 200 meters, question can be asked. Let's say that after 2 transit times, what's the value of the voltage, all right? Or you could be asked at the position 300 meters, how does the voltage change with respect to time? Okay. These are the questions that can be asked. So you can start with a scenario where you have 200 meters, and after 2 transit times from the time your voltage was launched to the left hand side. So all you need to do is you have to draw a line going from top to bottom like this. And as you go down, you need to simply add the voltages that you are going to be encountering. Okay. So you will be having 30 volts, okay, coming from the source side, 10 volts coming back from the load side. So at that instant of time, say after 2 transit times at z equal to 200 meters, you will be having 40 volts. Okay. So okay. Another thing that can be done is say at a position 300 meters or so, right, can be asked, how does the voltage evolve from 0 to 6 transit times? Okay. So the graph that is asked is draw the evolution of voltage is what's asked. Okay. So the graph that's asked is on the y axis you will be having voltage, on the x axis you will be having time in units of transit time. So you can mark it as tau, 2 tau, 3 tau, 4 tau. Okay. So we can look at this diagram and then say that the incident voltage, okay, is going to reach this point, okay, at some instant of time, and that is going to be 3/4 of your transit time, because 300 meters out of 400 meters, 3/4 of your transit time is going to reach. So till then the voltage will be 0 there, and once it reaches 3/4 of a transit time, the voltage will go up to 30 volts, which is your incident voltage. Okay. And after that, if you look at the bounce diagram, it remains at 30 volts, okay, because the source is continuously supplying 30 volts, right? It remains as 30 volts, and then after some time 10 volts get added to it. So that means you have to calculate the time that it took to go here and then come back, all right, and then you will have to add 10 volts at that place. So this is 100 meters, this is another 100 meters, 200 meters, that is half the transit time. Okay. So, you can go ahead 3 tau by 4 and half the transit time. So, that is going to be 5 tau by 4, all right. So, till that place your voltage is going to remain fixed at 30 volts, and then at that point it is going to spike to 40 volts. Okay. And then it remains as such for a while, all right. So, then you have the 10 volts going here, right. So, it remains at 40 volts till this wave actually goes from this point at 300 meters, goes to the source side, gets reflected and comes back. So, this is going to be a 300 meters and a 300 meters, that is going to be about 600 meters, all right. So, it is one transit time plus another half a transit time. So, 1.5 transit times from this place, you will be subtracting the 10 volts. Okay. So, we will take the diagram. So, from here one transit time will be 60 by 4 and half will be 6 t by 4 plus another something. So, that becomes 1.5 transit times is going to be somewhere about here. It is going to drop down to 30 volts again, all right. And then one can keep drawing as you go from top to bottom in your bounce diagram how the voltage is going to evolve. So, a typical question that can be asked is draw the evolution of the voltage, all right. And there can be other questions as to is it possible that the voltage in the transmission line is higher than what you supplied. Obviously, here we supplied only 30 volts because of the way it is configured, the way you have the source and the load resistances connected, you can have 40 volts in your transmission line at some point of time. So, if one were to design insulation for your cables, you will have to be aware of what kinds of values of voltages are possible and then decide accordingly what material to use. Okay. So, this is a bounce diagram and this is how you will draw the time evolution of voltage. More questions can also be asked. For example, you can always ask that what would the current bounce diagram look like? Okay. You could construct a current bounce diagram. One can also ask what would the evolution of current look like. Okay. So, but those are not very commonly asked questions. So, just for curiosity you can go back and try. Okay. So, I think at this point you should be very comfortable with dealing with these aspects of the transmission line. You should be able to calculate the transit time, characteristic resistance. If you know the source resistance and the load resistance, you should be able to calculate the reflection coefficients. You should be able to tell whether the voltage is going to have a positive sign or a negative sign going from one side to another side. You should be able to draw the time evolution of voltage in a transmission line, and you should be able to do some basic simulation to validate for these ideal cases. Thus far we have not considered any termination in your simulation, that is we did not put load resistance is equal to say 150 ohms or something like that, but you should be able to at least guess for an open circuit and short circuit what quantity will flip, what will not flip. Okay. So, at this point that is where you should be. Okay. Now, what are we going to do next? Towards the end of the class, I was telling that you could be a little bit more creative in the way you set up the source. So, I will go back to the simulation, all right. So, I will just change a few portions of these simulations. So far we have not dealt with frequency at all in our lectures. So, we will be trying to see AC steady state transmission lines and how they are working. So, I am just giving a sinusoidal input. So, you will be having a transmission line excited with a sinusoid, and we are going to make steady state analysis of this kind of configuration. And we will also be doing the same thing as what we did. We will be calculating characteristic impedance instead of characteristic resistance, right, and we will be calculating reflection coefficient, which will have signs positive and negative. On top of that, we are also going to see if it is possible to have phase for a reflection coefficient other than 180 or 0 degrees. And let me increase the time a little bit and show you what we are going towards. Right. Okay. When you excite it with sinusoid, some peculiar things will start to happen and we will have to analyze them. Right. So, here the voltage wave is traveling from one side to the other side. It is going to get reflected completely on the right hand side and it is going to superpose and you are going to get what are known as standing waves. Okay. There will be some specific nodes, specific antinodes for your standing waves and we are going to deal with them. On top of that, we are going to also understand how the impedance of a transmission line will change with length, because some portions are going to have always say 0 voltage or some portions will have 0 current. What does it mean to have impedances? Does the impedance vary across the length of the transmission line? If it does vary, how does it vary? All right. And then we will be starting to look at different lengths of transmission lines, what kind of impedances they will have and how to make use of them. This is the plan for the next few lectures. So, I'll stop here, right. Go back and try plugging in some different values for load resistance, source resistance, see if you're comfortable doing a few problems. Your tutorial will also be having some problems along this line, all right, so that you can just practice calculating different things.